Let's say we have the square root of -9. We can break this down into the square root of 9 times the square root of -1. Okay, we know the square root of 9 is 3. So plus or minus 3. And we multiply this by -1. The square root of -1 has no real solution, but we have entered a number to solve this. We're going to say that the square root of -1 is equal to I, the imaginary unit. So let's put this back into here. Our answer is plus or minus 3i. Let's do another one, just to get a feel for this new number. So we have the square root of -64. That's equal to, and you can do this product on radicals. You can break it down into its factors. So let's do square root of 64 times the square root of -1. We know square root of 64 is plus or minus, can't forget the plus or minus, 8 times square root of -1. And we're, by definition, I is equal to the square root of -1. So you can put it right here, plus or minus 8i. We can use it in the quadratic formula. Let's see, x squared plus x plus 1 is equal to 0. Let's plug these numbers into the quadratic formula. -b plus or minus, real quick, plus minus the square root of b squared is 4ac divided by 2a. Okay, substituting, we're going to have -1 plus or minus 1 squared minus 4. Since it's just 4 divided by 2 times a, which is just 2. This is -1/2 plus or minus the square root of -3 divided by 2. Okay, this part is okay. -1/2 plus or minus the square root of -3. We can break that down into the square root of 3 times the square root of -1. Substitute our I, and we have the square root of 3 times I, plus or minus I times square root of 3 divided by 2. This is our solution to the quadratic. And when we have an imaginary number mixed in with a real number, this is called a complex number. So our real numbers are of the form a, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And our imaginary numbers are the form bi, like 2i, 3i, I. These are all imaginary numbers. But when we mix them together, a plus bi, this is a complex number. Okay. So some properties of complex numbers. If we want to add complex numbers, we can just add part by part. Let's say we have 3 plus 6i plus 5 plus 11i. We just do it part by part. Add the reals and add the imaginaries. So 3 plus 5 is 8. And 6 plus 6i plus 11i is going to be 17i. And same thing, we have a number scaling a complex number, like 2 times 3 plus 4i. We can just distribute the 2. 6 plus 8i. Or 3 times 4i. This one's even simpler. Just going to be 12i. But something special happens when we multiply complex numbers by each other. So we have 3 plus 4i times 5 plus 6i. I'm going to use an area model for this, but you can FOIL. Three, 4i, 5, 6i. We're just going to multiply. 15 plus 5 times 4i plus 20i. 3 times 6i is 18i. But now we have 4i times 6i. Let's write that out. 4i times 6i. This is going to be 24i squared. We can simplify I squared. If we remember that I, we define it to be the square root of -1. If we square both sides, we get I squared is equal to -1. So let's put that back into here. Okay, so 24 times -1 is -24. Put that back into here. Minus 24. And we're going to add all these parts. It's like the area model system. Okay, so 15 plus 18i plus 20i is plus 38i minus 24. Okay, and we combine the real parts now. 15 minus 24 is going to be minus 9. So minus 9 plus 38i is the product of these two complex numbers. And here you would have gotten the same result if you FOILed. I just like the area method because it's more visual. Okay, and now let's say for our last case that you have division. So 3 plus 4i divided by, say, 7 plus 12i. Okay. What we're going to do is multiply by the complex conjugate. A conjugate is simply when you switch the signs between an expression. So let's do that for a denominator. 7 minus 12i. This is the complex conjugate. Divided by 7 minus 12i. And here we're not actually changing the value of this expression, because this thing in theory is just equal to 1. It's just the same thing divided by itself. Okay, so now we're going to multiply these expressions. Let's see what happens. Okay, so we have 3 plus 4i, 3, 4i, and 7 minus 12i. This is just 21, 7 times 3. 3 times -12i is going to be -36i. 4i times 7 is just 28i. Okay, and 4i times -12i is -48 times I squared. And since I squared is -1, it's -48 times -1 is equal to 48. 48. Okay, let's clear this up. Add these. So 21 plus 48 is going to be 59. 59 plus 28i minus 36i is minus 8i. That's going to be our numerator. 59 minus 8i. And for the denominator, if you didn't recognize this as a difference of squares, you can do the same thing again. 7 plus 12i. 7 minus 12i. Okay, 7 times 7 is 49. 7 times 12i is going to be 84i. 7 times negative 12i is going to be minus 84i. Okay, and 12i times negative 12i. Negative 144 times I squared. And when I'm dealing with I like to be very careful like this, so I don't make a sign error. Okay, and I squared is negative 1. So negative 144 times negative 1 is 144. Okay, so these 84i minus 84i, these just cancel out. So then we have 144 plus 49. And plus 4 is 13. 1, 9, 193. Okay, so our denominator, is going to be 193. And distributing that, we can just write this as 59 divided by 193 minus 8i divided by 193. This is the quotient of these two complex numbers. And so is this one. These are both okay forms. Okay. And just in case, let's say we have exponentiation, like just patterns of I squared, I cubed, and I to the fourth. Let's say even I to the fifth. Okay, I can stay as is. It's just square root of negative 1. You can write either one. I squared is I times I. So the square root of negative 1 times the square root of negative 1 is going to be negative 1. So I squared is negative 1. I cubed, it should just be I squared times I. We know I squared is negative 1, so it's just negative 1 times I. So that means I cubed is negative I. And now for I to the fourth, that should be equal to I squared times I squared. So negative 1 times negative 1 is equal to 1. This is how you would approach the 4 basic exponents of I. And now for the last one. I to the fifth. That's just going to be I to the fourth times I. And if we know I to the fourth is 1, this is just going to be 1 times I is equal to I. This is how you would approach the exponentiation problem with imaginaries.